Welcome to PowerPoint Chapter 8b, our look at wind systems around the world and global circulation. We're going to talk about some regional and local winds, which have a bearing on precipitation or the lack thereof in some parts of the world. And we start with one of the most dominant and dramatic circulations in the entire world. It's called the monsoon, the Asian monsoon specifically. Now, when you think of monsoon, what do you think of? Well, you probably think of a lot of rain. Well, that's only part of the story. The word comes from the Arabic word mausim, which means seasons, literally a shift in the winds with the changing seasons, wind coming from a different direction. This is most dramatic over the Indian subcontinent and South Asia, and for that matter, over Southeast Asia. Now, the dry part of the monsoon, the winter monsoon, there's cold air over Asia because of Arctic air from Siberia. That causes high pressure there. The air flows from the continent toward the coast. The water is warmer relative to the land, so there's low pressure along the coast, and it draws the air toward the land. This produces dry weather from December through February, which is depicted in our next slide, figure 8.13a. Then in the summer, it's just the opposite. The Eurasian continent becomes hot, so you have low pressure, not high pressure, and that tends to draw warm, moist air up from the Bay of Bengal, the South China Sea, and the Arabian Sea, and that warm, moist air slams up to the southern slopes of the Himalayas. A tremendous amount of lifting by topography, and it rains, and it rains, and it rains, and guess what? It rains some more. The rains can be drenching and flooding, but they're vital to agriculture in this part of the world, both South Asia and Southeast Asia, and without them, agriculture as they know it cannot exist. So there is a winter dry pattern to the South Asian monsoon and a summer wet pattern to the South Asian monsoon. One of the wettest places in the world associated with the Asian monsoon happens to be Cherrapunji, India, which is in the northeastern part of India, just north of the border between India and Bangladesh. They have a distinct dry pattern in winter, as you can see this climate graph showing monthly mean precipitation from January through December, and a distinct wet summer climate. Can you imagine this? The average annual precipitation in Cherrapunji is an astounding 425 inches of rain a year. Now, to put this in perspective, Fresno receives 11.5 inches of rain a year. Now, that's quite a contrast, wouldn't you agree? So that's the South Asian monsoon. Now, believe it or not, there is a North American monsoon. It's rather slight compared to the South Asian monsoon, no question. But here's how this works. In the summertime, high pressure in the upper levels of the atmosphere tends to settle in more or less over the Four Corners area of the southwestern United States. You know, that's where Utah and Colorado and New Mexico and Arizona come together. There's an upper level high here, very warm descending air. The wind flow, the circulation around that upper high is from the southeast over the southwestern United States, if you get my drift. And what that does is it brings moisture in from the Gulf of Mexico and from the Gulf of California and the tropical Pacific, and combined with the very hot, dry air over the desert southwest at that time of year, can cause torrential thunderstorms. So oddly enough, a place like Tucson, Arizona, you notice on this climate graph, which comes from The Atmosphere, the textbook by Lutens and Tarbuck, not your textbook, 11th edition, but a different book that's showing something nonetheless. Look at the monthly mean precipitation for July in Tucson, Arizona. That's when they have their wettest month. That is the North American monsoon. Now, let's talk about local and regional winds from this perspective, a very simple thermal circulation, which is called the sea breeze versus a land breeze. If you've gone to the coast in California in the summer, you certainly have experienced a sea breeze. And on our hottest summer days here in the interior of California, we hope that there's enough of that breeze getting through the gaps and passes of the coast range to at least make our summer nights more comfortable and more sleepable, if you will, because the hot nights are certainly uncomfortable for sleeping and you have to close your windows and run your air conditioner. So a sea breeze and a land breeze is a basic thermal circulation. During the day, land heats up more quickly than the water. We've discussed that. So with land hotter than the water, you have low pressure over land and higher pressure over the water. It tends to bring the air from the water to the interior, and that's the sea breeze part of the component. The leading edge of the sea breeze is called the sea breeze front. This causes places along our coast here in California in the summertime to sometimes have the high temperature before noon. Now, during the night, the opposite can often occur. Obviously, the land is going to cool off faster than the water. So by late night and early morning toward daybreak, it's not uncommon for you to actually get a drift of air from the land toward the ocean. And the reverse of the sea breeze then is called a land breeze. In Florida, they have a unique case because the Florida Peninsula is surrounded by water on all three sides. You, of course, have the Gulf of Mexico to the west. You have the Strait of Florida to the south, and you have the Atlantic Ocean to the east. So on any given day in Florida, except for wintertime, you're going to get a convergence of the sea breeze from the Gulf of Mexico and the sea breeze from the Atlantic Ocean, and somewhere there are going to be thunderstorms. The tough thing for forecasters to figure out on a daily basis is exactly where those thunderstorms are going to crackle. But when sea breeze fronts converge, such as over Florida, thunderstorms can easily develop. Now let's talk about valley and mountain breezes. Maybe many of you don't know this, but the highest in elevation sailboat race in North America is held every July right here in Fresno County in Huntington Lake. It's called the High Sierra Regatta. Maybe you've been there. I think it's like the first and third or second and fourth weekends in July where people who go sailing take their sailboats up to Huntington Lake, and they depend on that afternoon breeze coming up the Big Creek Canyon from the San Joaquin Valley to propel their pretty sailboats. And did you know there's actually a Fresno Yacht Club? Yeah, it's true. In any case, I digress. So during the day, the slopes of the high mountains, which don't have vegetation on them, that are just dirt and granite, heat up very rapidly, and that tends to suck air up from much lower elevations, so the breeze comes from the lower elevations through the canyons up to the higher elevations. That's known as a valley breeze. At night, those same mountain slopes that don't have vegetation, that are just dirt or granite, cool off the fastest, so the air sinks and flows down in the reverse. So in the late night and early morning, you have the opposite of that, which is called a mountain breeze. Now, as this graphic depicts, if you have enough moisture in the air and enough convergence on either side of the mountain on a day when there is a valley breeze, you can get enough convergence to produce some cumulus clouds over the higher terrain. Here's another extreme kind of wind, which we only rarely experience here in this part of California, and I'll talk about that in a minute. It's called a katabatic wind. This comes from the Greek word katabatik, which means to descend or fall, kind of like water in a waterfall. Think of Yosemite Falls. Here are the ideal conditions. If you have a high mountain range or elevated plateau, which is very cold, and it's surrounded by mountains, with an opening or a pass that now allows cold air to rapidly travel downhill, cold, heavy air at the higher elevations can then easily flow toward the lower elevations, and it heats by compression and warms up. So if you have a minus 25 Celsius air mass on that high, cold mountain plateau, it can warm up to as much as minus 4 Celsius by the time it gets to the lower elevation in this graphic, 8.21. There are local names for these katabatic winds in different places in the world. Along the mountains of Croatia and the Adriatic Sea across Italy, they call it the Bora. In the Alps, descending to the French Riviera, they call it the Mistral. In Oregon and Washington, through the Columbia River Basin or Columbia River Gorge, they call it the Coho. And here in California, we occasionally have a katabatic wind, which is called the mono wind of the western Sierra Nevada. Now, this is going to take a little bit of remembering on your part, but if you can remember Thursday, December 1st, 2011, if you were a student here on Fresno State's campus on that day, Thursday, December 1st, 2011, you might remember it was a very windy day. We had 40-mile-an-hour winds, and there were trees down all over the place. Oddly enough, it was a very warm day. It was 69 degrees that day. But in that same afternoon that it was 69 Fahrenheit in Fresno, it was slightly below zero at the top of Mammoth Mountain. That's a perfect example of a katabatic wind, cold, heavy air descending through mountain passes and warming up as it descends to the lower elevations. Well, that was a mono wind, and that occasionally happens here on the western slopes of the Sierra Nevada, where cold, heavy air from the Great Basin can descend through the higher passes of the Sierra Nevada and head to the San Joaquin Valley. These graphics come from a study that a man named Russia did back in 1974. It was a fire weather study for the National Weather Service, but it shows how the winds move from east to west toward the San Joaquin Valley floor, but they actually rarely reach the San Joaquin Valley. These mono winds can exceed 100 miles an hour in gusts, and can roar through Yosemite Valley and knock trees down like matchsticks. On the early morning of February 19th in 1988 in Yosemite Valley, Mono winds toppled trees on top of cabins and resulted tragically in the death of a 9-year-old girl. This photo comes from the Yosemite National Park Research Library and Archives. So this is a type of katabatic wind in California called the mono wind of the western Sierra Nevada. Then in the eastern part of the Rockies, there is something called the Chinook wind, which you might have heard about. It's a strong wind that comes down the eastern slopes of the Rocky Mountains. It can warm up very rapidly on the leeward slopes. If you have strong westerly winds above the Rocky Mountains and they descend rapidly down toward Denver and out to the Great Plains, the air heats adiabatically and compresses, and so they have warmer temperatures. If you have clouds and precipitation on the windward side, the western slopes of the Rockies, that can actually aid and abet, so to speak, compressional heating on the leeward side and enhance this Chinook wind effect. 8.22 shows the dynamics from your textbook of a Chinook wind on the Rocky Mountains and how the air can really warm up on the eastern side, the leeward side. And the picture, 8.23, shows a Chinook wall cloud viewed from the eastern slopes of the Rockies looking toward the western slopes of the Rockies. These Chinooks can also produce some bizarre effects because if you have cold air in the Great Plains, it can slosh back and forth like water in a bathtub, and people in the foothills west of Denver, or maybe in Boulder, can experience tremendous temperature differences in just a few short minutes or a few short hours as that boundary of cold air sort of sloshes around because of the Chinooks on the Great Plains. Then the infamous Santa Ana winds of Southern California, which you no doubt know something about. You have cold, heavy air over the Great Basin. It seeks the path of least resistance and flows in the late fall and wintertime toward the ocean because the ocean is warmer than the land. The air heats up compressionally as it descends and funnels through the mountain canyons. They're called Santa Ana winds because those winds are particularly strong in Santa Ana Canyon in Orange County. Here is a map from a particular January recently from your textbook where you have temperatures in the 40s and 50s over the Great Basin, which resulted in temperatures in the 80s along the Southern California coast because of the compressional heating of the Santa Ana winds. Here's a cross-section, 8.26, of the surface pressure pattern, which is often associated with the Santa Ana winds. It's kind of a little cartoon, a little illustration to show you how this works. This is a dramatic photo from your book. It's I think a half-kilometer resolution visible image, which shows strong northeasterly Santa Ana winds effects October 23, 2007, blowing smoke from massive wildfires. Each wildfire is noted with a red dot. The names of towns are in the gray dots, and how that smoke is blowing over and out over the Pacific Ocean. Now, in Northern California, we occasionally have similar offshore winds along the northern and central California coast. So they sometimes will call them Diablo winds. It's the same meteorologic setup as the Santa Ana winds, resulting in terrible fires. The firestorms in the Oakland Hills, one was in September 1923, the other most recently in October 1991, as depicted by figure 8.29 in your textbook. On your own, click on this hyperlink and you can see how frantic people were when they were trying to evacuate the Oakland Hills during that firestorm. Just astounding. Over 3,000 homes damaged and 25 people died in that Oakland Hills firestorm of October 1991. Other extreme winds of interest include dust storms caused by strong downdrafts from dissipating thunderstorms called haboobs, from the Arabic word hebi, or blown. If you've driven across the Fresno State Farm on Bullard Avenue on a hot late spring or summer day, you no doubt over the fields that don't have vegetation have seen occasionally what we call a dust devil. No surprise there. There are a number of names for the hot, dry winds as depicted in figure 8.34 that blow from Africa across the Mediterranean toward Europe, and you can see those names in the arrows. And sometimes from the Sahara, enough dust becomes airborne in high elevations of the atmosphere to get sucked into mid-latitude cyclone-type storms off the southwest coast of Europe. This one is depicted off the coast of Spain, as you can see. This is a tremendous dust storm that occurred in Bakersfield on Tuesday, December 20th, 1977. I lived through that dust storm. The aerial view at left from Sam Chase in the National Weather Service shows what the dust looked like above the town of Arvin. The graphic on the right shows the weather map for that dust storm. It was quite a time. I will never forget it in my entire life. And it resulted a few weeks later in a big increase in cases of valley fever because of the spores that traveled in that airborne dust. All right, this ends Chapter 8B PowerPoint.